do want to get to the hot topic of the day, because the
Absolutely.
billions of gallons of wastewater pouring into the planet are creating a challenge for remote areas, as well as for the sewage treatment plants, even the industrial areas. And Malcolm, our guest speaker, is working both in remote areas. He comes from Nigeria, has a heart for Africa and a heart for all of those who don't have resources. But he has used his heart to serve and engage and educate with more than 60 presentations he's given to the Water Environment Federation, and speaking across the globe, the World Water Tech Organization, to educate others on what he believes could be the future of wastewater, an area that has lacked innovation, but definitely needs it. And another aspect to Malcolm's expertise is that he is a business optimizer. So knowing that many of you are running wastewater or water treatment businesses, and Malcolm has experience with data and analytics, brings a tremendous expertise. He holds a PhD in chemical engineering from Cambridge University, an MBA from the University of Chicago Booth School of Business, and he has just tremendous experience with oxygenation technologies, advanced treatment methods, biosolids reduction technologies, biogas enhancement, and bioremediation and modeling. So he received the 2016 WEF Rudolph Industrial Waste Medal because of his work, and he's authored over 60 presentations. When I heard him, it was perhaps the best presentation I had ever heard in the water industry. And I am just thrilled to also see Margaret Mena just joined. She has just retired, amazing contributor to Kenya's wastewater efforts, and now hopes to lend her knowledge and expertise to the world. So Margaret Mena, welcome. You are just in time to hear Malcolm Fabiyi with his presentation, Rethinking Wastewater Treatment. So thank you, Malcolm. We'll have 30 minutes of the presentation and then time for Q&A and discussion up until the bottom of the hour. No, it would be the top of the hour, 8 p.m. in India, or depending on where you are, we're 90 minutes in for this total presentation. So Malcolm, over to you.
Thank you very much, Mary. And it's a pleasure and a privilege as well to have the opportunity to speak with everybody today. I think for those of us who work in the water space, I think it's a calling. It's not a career for me. It's a calling. I think there's a certain passion that we feel about being able to wake up every day and know that the work that we do actually makes an impact, not just for our families, but for our communities, for the environment, and for the world. So this is something I'm really passionate about. So my topic for today, with some suggestions from Harry, was around the notion of rethinking wastewater treatment. And quite frankly, for the almost 30 years in which I've been working in this space, it's a realization that I came to maybe halfway into my career in the wastewater space, that there's a need for us to, quite frankly, rethink the way we approach water and wastewater treatment. A lot of the learnings that I've had is that this is one of those industries where we have responded to needs. So wastewater treatment, it doesn't matter where you are in the world. The remediation space is not a space where we had solutions and then applied those solutions to problems. In almost every case, we had problems and we were pushed to respond to those problems. I am reminded always that water and wastewater treatment is oftentimes not revenue generating. It is always a cost. There's always a cost to treatment, and therefore very few people are willing to act proactively. So oftentimes it is regulation that pushes us to do stuff. Oftentimes we don't act until the environment starts falling apart around us. But what I thought I would do today was basically to approach the conversation in 5 major areas. So the first one is I'll share some of the experiences that I've had in the water space. I think sharing that background will provide folks with the context for where I come from, and the context for how I approach the water and wastewater treatment space, and probably also provide some good context for what has informed the positions that I take now about what it would take and what would be necessary in terms of how we rethink how we approach water treatment. I'll talk about some relevant fundamentals. I recognize that I'm talking to a group of experts, but I think sometimes it's also good for us to just level set and talk about some of these fundamentals. And simple as they might seem, I think it is those fundamentals also, the simplicity of the tools we have. We have a very complex problem, but the reality is there's a simplicity to how that treatment happens. It's mostly based on microbiology. It's microbes. It's simple. These are very simple organisms, but also very complex in the way that they behave. And there are many complex interactions that take place in the water space. And I think grounding ourselves in some of those fundamentals, at least in the way that I understand them, I think would be helpful. The idea of microbes and why that immense resource that nature has provided to us, how we can leverage that to better effect. Bioaugmentation, it's in the last decade of my activities, in the 3 decades that I've been in the water space, in the last 10 years of that experience, it's mostly been around this idea of bioaugmentation, the idea of tweaking what we have and leveraging our increasing knowledge of microbiology and how microbes behave to enhance what treatment units can do. Prior to this, the approach had always been that you had to engineer bigger solutions. There had to be more pumping and bigger systems and larger reactors. But once we understand what microbes do, there are things we could actually use those microbes for without really changing much about what that treatment space and that treatment environment looked like. And then I would share some thoughts about the future of water treatment, some of the work that we're doing in OptimaBiome, and then we'll go into the Q&A session. So as I look over the last 20 to 30 years of my involvement in the space, there are, I think, 5 big areas of engagement and activity that have shaped my approach to water. Mary was gracious in our introduction. My background is in chemical engineering. I studied photochemical reactor design and engineering in Cambridge, mostly focused on water treatment, basically taking industrial wastewater, in this case, nuclear wastewater, and treating that. So that was my initial entry into the project. And the idea there was, how do we take things like UV light, readily available energy, and just leverage that for treatment to reduce cost, but also to allow us to deal with really challenging situations. Shortly after I left Cambridge, I joined a company called Praxair at the time. It's now part of a global industrial gas company called Linde. The manufacturer of industrial gas is obviously, when you're doing industrial research, what your employers want you to do is to take the products they manufacture and find applications for those in industry. And the major products we manufactured were things like oxygen. We made things like, manufactured things like CO2, and we were looking for applications. And when you make oxygen, the most obvious application is the aeration process in wastewater treatment. There's a lot of oxygen utilized by those microbes. And I spent quite a lot of time in Linde, Praxair, looking at things like oxygenation, a lot of work in industrial, wastewater, municipal wastewater treatment. Harry, you mentioned about 30-something plus billion liters a day. In the US, we treat 40 billion gallons a day of sewage, of municipal. That's just municipal. There's another almost 20 billion that is uniquely industrial. And then there's even more agricultural water usage that is completely outside of the numbers that I've mentioned. So it's an enormous, incredible amount of water that is utilized. But my experience in Linde Praxair exposed me to a significant number of technologies, a significant number of spaces, the immense challenges of water treatment, the challenges that increasing regulation brings to bear, and then, obviously processes like digestion, And the fact that in almost every situation, we're dealing with fundamental mass transfer issues. If you think about a typical wastewater treatment plant, there's the microbes themselves and just the mass transfer challenges of getting the organic material that these microbes are going to degrade to the microbe. You need, efficient mass transfer processes to make that happen. But at the same time, if you're using things like oxygen, you need to make sure that those molecules are getting to those microbes. So it's an immense mass transport problem. I also had the good fortune of being involved with a company called Hydromantis. I led their operations in the US. This is one of, I think, 2 companies in the world that are leading that are at the forefront of the application of mechanistic models in the water and wastewater treatment space. They have a platform called, they have several platforms that are utilized for biokinetic process modeling. They do fate and transport, what happens to not just broad things like COD, which are the high-level terms we use to track what's happening with organic materials, but they go down to the level of specific molecules, because there are some aspects of the regulatory process, especially here in the US, where the interest is not just in how much have you treated. The interest is also in what has happened to some specific organic compounds. So odor and air emissions, we looked at things like digital twin models and all of that. And as I said, in the last 10 years, my focus has been in bioaugmentation. I worked with a company called Drylet. And what Drylet does is basically bioremediation. How do you take microbes, go into existing systems without changing anything, without putting in more capital, without building more treatment footprint, without any additional pumping? How do you go into those systems with a keen understanding of microbiology and still find ways to optimize the processes? And in the last year, I have... Sorry?
I'm really sorry about this. One moment, please. Yeah. Please mute everybody. I'm very sorry about that, man.
No problem, no problem. Okay. And in the last year, I have, so for the last year, I've been, I run my own startup called OptimaBiome, and what we do in OptimaBiome is basically just leverage biology for bringing environmental and climate solutions. So in all of this time, this is just a selection of some of the types of processes that I've essentially worked with. So a lot of oxidative type processes, a lot of filtration, adsorption type systems, done a lot with oxygen, enhancing mass transfer, trying to improve mass transfer processes. We've worked with membrane filtration, with different types of biofilm systems, just to enhance, how you intensify biological processes. Conventional aeration, done, work with ozone, a lot of work with digestion. And as I indicated, one thing that has tied all these different processes together is just the modeling aspects. We have, I think we've come a really long way, and I'll talk more about this in future slides, where we now have a deeper, keener understanding of what is going on in these treatment processes. So if I jump straight into sewage treatment, the traditional approach we have to treating sewage is exactly almost about 110 years old now. It was developed by 2 gentlemen, Harden and Lockett, based out of the UK in 1914. And the reality is the process has changed very little from what they did. The only changes, the major changes that have happened have been around what you do in secondary treatment. So for almost 60 years, so from about 1914 till about 1974, at least in the US, the exclusive focus of wastewater treatment was just removing COD. And if all you're trying to do is remove COD, so there are 3 major challenges we have in a wastewater system. We have carbon, we have nitrogen, we have phosphorus. And, we spent the first 60, 70 years just focused on removing carbon. If all you want to do is remove carbon, they're very, all we need to do very simply is capture about 50% of the carbon coming into a wastewater plant is in the form of solids, mostly fecal waste. So if we have grit removal systems that remove sand, if we have primary clarifiers, this is sufficient to remove about 50, 60% of your organic material. But if you're trying to remove nitrogen and phosphorus, that introduces additional complexities. And so most of the process changes that have happened in the last, especially in the last 20 years in the wastewater space have been around developing, extending the process so that we can do things like nitrification, denitrification. We can do things like luxury phosphorus removal, encourage the growth of phosphorus accumulating organisms and things like that. But the fundamental process has not changed that much. In almost every process, in every biological wastewater process, whether it's aerobic or anaerobic, you're going to generate sludge. What has happened that has changed in the last decade or so has been that in the past, we were all prepared to take the sludge and take it to a landfill. Now there's a recognition that locked up in that sludge is organic material, is energy, and there's no, why waste energy? Why take it to a landfill and have fugitive methane emissions, leachate result from that when you can actually tap into that energy source? The other thing that we've learned, and I'm grateful to have been part of this development in the last decade or so, has been that we now have a keener understanding of all the complex elements that go into the wastewater treatment process. As I indicated, I was fortunate to work with Hydromantis, leading their activities in the US. The CEO of Hydromantis is a gentleman who is actually now visiting family in India called Dr. Rajiv Goel. And, we have a keener understanding of the biokinetics that governs how microbes behave. We understand now that the thousands and thousands of microbes in a wastewater treatment process each have their own unique biokinetic rates. Some of them double every 2 hours, some of them double every 2 days. Somehow you have to find a way to balance those complexities. In some places, we're precipitating material. Sometimes we're using different chemicals. We're moving water. We're moving water that has solids. We're moving water that has biological solids that have a density that's close to that of water. But at the same time, that water, as it moves through a sewer, might actually also be moving sand and grit materials. And as you're moving through the process, some things are settling out. Sometimes you're forming new solids. It's a complex system. But thankfully, we have been able to develop tools that allow us to handle that complexity so that whether we're dealing with a plant that treats 1 billion gallons a day, like we have in the city of Chicago, or whether we're dealing with a small decentralized system that's supporting a school that has 400 people, there are now tools that we can use to basically design those systems to enable us understand precisely what they can do and how it can be done and what the footprint would be and essentially what would be needed to get it done. So now to the fundamentals. At the end of the day, all we're trying to do in wastewater treatment from a biological perspective is we're trying to take organic material that has carbon and leverage the metabolism of microbes. Exposed to a carbon source, microbes are going to consume that carbon source. That treatment is either going to happen aerobically or it would happen anaerobically. If it happens aerobically, our end products would likely have a significant amount of CO2, and we will always form some excess sludge. If it happens anaerobically, our main output will have methane. There will also be a little bit of CO2, but we will also have some sludge, less sludge, because the anaerobic process, is energetically less efficient, which is an advantage for us because that generates less sludge. At the end of the day, that sludge would have to be treated. So the less sludge we have, the better. Anaerobic processes in general tend to provide a lower yield relative to the amount of COD, the chemical oxygen demand that is reduced. So we know microbes are effective. We know they're extremely effective. We know they can remediate a broad range of contaminants. And one of the and if you look at the pros and cons of the process, you know, the main advantage of the biological approach is we're leveraging nature. Microbes were here on Earth long before humans came here. They have learned to metabolize most things. There's practically nothing that microbes can't deal with. The only challenges we're facing now are some new molecules we've created. So things like PFAS are a little difficult for microbes to deal with because they're new molecules. We're just starting to find microbes that can metabolize some of those materials. We're finding it a little difficult to have microbes that can metabolize things like artificial sugars, for example, in wastewater treatment systems, because these are new. They're new challenges to microbes. But interestingly, we're also starting to find that there are microbes that have started to adapt. So when you look at some wastewater plants, and I did this work in the last 5 to 10 years, we were seeing, you know, things like aspartame and some of these new sugar molecules, sucralose, just going through the process almost completely untouched. But now we're starting to see microbes adapt to them. So microbes are remarkably adaptable. So the beauty of the process is it's cost effective, it's robust, it's flexible. Any wastewater treatment plant, you know, we do a lot of genomics. There's thousands of bacteria. If one fails, there's another that's going to take over and get the work done. And then obviously it's publicly accepted. Disadvantages, though, is that it's not everything that is biodegradable or readily biodegradable. So take your typical sewage. Roughly half of what the biggest portion of what we excrete is what comes out of a home is actually solid. So 50% of our sewage waste in a house is actually it's solid material. Now that solid material is biodegradable, but it's going to take time for that biodegradation to take place. It has to be hydrolyzed. A microbe can't feed on anything bigger than itself. So if a microbe is about 0.1 to 1 micron in size, then it means those large particles that we're excreting, you know, that are 100, 200, 300 microns in size, that make up those undigested food materials or make up other microbes, they have to break down. They have to become solubilized. It takes time for that to happen. So we're challenged by the fact that not everything is biodegradable or readily biodegradable. It has a big impact on what we're able to do and the timescales. And a lot of the challenges we found is, you know, although microbes are effective, extremely effective, you know, that I love to look at this image. The microbe can't do treatment unless the food material, the material we're trying to treat, somehow passes through this cell wall. In order to pass through this cell wall, there are all types of challenges you need to have. First, it has to be small enough to pass through, so it has to be solubilized. But the second thing is that your mass transfer systems have to ensure that you're moving material from areas of high concentration to areas of lower concentration. You're bringing it close to the microbe, which requires, in some cases, movement. The ability to be able to put some motion around the microbes to transport those materials. So remarkable process, but then we're also some issues we have to deal with. And then just the dizzying array of microbes and functions that we require. If we think about just sewage, what's coming from somebody's home, the challenges we face are immense. So we have carbon. In order to degrade carbon, we need things like traditional heterotrophic biomass. We need facultative organisms. A lot of organisms are facultative, especially a lot of the organisms that are in the human digestive system. So our digestive tract, about half of fecal matter is microbes. Those microbes are mostly anaerobic inside of the human body, but they're facultative. So exposed to an oxygen-rich environment, those microbes can also metabolize. But in order to just treat what's coming out of a human's body, we need facultative and heterotrophic organisms to do COD removal. We need fermenting microbes to be able to help us break down some of those large molecules and help hydrolyze them. We need methanogens to take the products of that hydrolysis that have been turned into volatile fatty acids and convert that into methane. We need nitrifiers to take the organic nitrogen, which is in a bound form, and convert that into nitrates, because the only way nitrogen is treated is to convert it to a gas. That's the only way we can treat nitrogen. So how do you do that without doing some type of nitrification that converts organic nitrogen and ammonia into nitrates? And then we have other microbes, a lot of them heterotrophic, that are then able to take those nitrates and degrade them and use and basically use the oxygen from those nitrates in terms of reduction. We have ion-reducing bacteria, and in the industrial context, there are many of these bacteria systems that we've dealt with. You also find them a lot in digestion type systems. Halophiles, we do a lot of work, especially on the coastal area near the oceans, where there's a lot of seawater infiltration. There's a lot of halophiles, high salt tolerant organisms that need to be involved in the wastewater treatment process. Otherwise, those treatment systems are not going to be resilient because they have all this seawater infiltration and quite high levels of salinity. So just a dizzying array of microbes that we have to deal with. And these microbes, they provide resiliency, but they also provide challenges because each of them has a very different kinetics. Their growth rates are different. The environments and conditions they like are different. The halophiles like high salt environment. The alkaliphiles like high alkalinity. Many neutrophiles want to stay in a neutral range. All of these different conditions have these immense impacts on microbes. And what I've learned over the last, in my time serving in this space, I've just been the fact that there are these 8 factors that determine what our microbial consortia looks like. Many of these factors we actually don't have any control over in wastewater treatment. We don't have any control over the food. The food by definition is waste. So this is not like a brewery where we're feeding the microbes specific food and we're choosing what we feed them. It's wastewater. Today it might be fats, oils, and grease. Tomorrow it might be proteins. The day after it might be, it might just be some spillage that falls, through the sewer system. So the type of food we have is variable. The temperature can be variable, especially in places like the US where, it could be, it's in Chicago, it might be minus 21 day, the next day, but the bugs require the environment to be at about 25 degrees Celsius on average for them to function well. The retention time varies. It can vary just based on the fact that you have fluctuations in flow to a plant. If you have wastewater systems that are not separated from rainwater, the volume of material that's going in can have a 10x variation. So hydraulic retention time changes. We have plants that have small hydraulic retention time, some have longer retention times. The oxic environment, the ORP conditions, the nutrients that you have. In some instances, especially municipal sewage, we have all the nutrients we need because it turns out that what we feed on is also the same thing, is very similar to what the microbes want to feed on. So they have the nitrogen, the phosphorus they want. In most cases, we're trying to remove nitrogen and phosphorus. In the industrial context, there's almost always carbon, no nutrients. So we're actually needing to add nutrients. We're needing to add nitrogen, needing to add phosphorus to those industrial systems. The sludge age, it varies. If all I want to do, which was what we did for the first 60 years of wastewater treatment, if all I want to do is remove carbon, all I need is about 2 days of retention time. The average age of my bacteria doesn't need to exceed about 2 to 5 days in order for me to have effective, almost 100% COD removal. However, if I want to do nitrification, if I want nitrifiers to grow in the process, I cannot do that unless my average sludge age, the retention time for those microbes exceeds about 5 to 10 days. In fact, sometimes up to about 15 days because they grow more slowly. So that's a complication because now it means, I need to find ways of retaining microbes, which means I might need to increase the size of my basins, or it might mean I need to hold more material in inventory. And then the pH and the alkalinity, extremely, microbes are extremely sensitive to the pH, to all of these conditions. And we cannot always guarantee we would have this condition. So what options do we have? Well, bioremediation tends to be one thing we could do. So nature does whatever nature wants to do within the treatment system. And then one of the things I've learned to do over the last 10 years is leveraging microbes, identifying how best we can optimize the tools we have, and then tapping into nature. So if what I need are nitrifiers, then maybe I don't need to build bigger basins to get the nitrifiers. Maybe I just go back here and find some nitrifiers in nature, cultivate them someplace else, and then bring them into the process. If I need, so maybe what I need are halophiles, I probably don't need to expose my entire system to halophiles. I can see whatever hand nature has dealt me in my process, optimize it as best as possible, and then go find halophiles and bring those halophiles into the system. So it leads us to the other challenge that I've also been focused on in the last decade, which is if we're trying to optimize a wastewater treatment system without building more tanks, without increasing sludgeage, and we're going out to bring microbes that are not natural or native to the system through bioremediation. What it means is that we are trying to introduce into that process microbes that natural selection does not prefer. Because if those microbes were if the natural tendency was for those microbes to grow, we would not need to bioremediate. They would already be in the system. We would have optimized for them. So anytime we're doing bioremediation, it means we're trying to introduce into a system microbes that nature has not selected for, and it poses 4 problems. The first problem is that any microbial system we go into has acclimated microbes. There are, it has the bacteria themselves, it has viruses, phagal organisms, phages, viruses that are native to the system that the microbes must be adapted to. And then it has other organisms. So the first problem we have is if we introduce these new microbes, one possibility is they get killed by things that are smaller than them, by viruses. The second problem we have is if we introduce these microbes new to the system, because we're trying to enhance the process, microbes are in the region of 0.5 to 1 micron in size. And a healthy microbial ecosystem would have things like rotifers, it would have water bears, it would have amoeba, paramecia, organisms that are 50, 100 microns in size that feed on the bacterial cells. So if we're introducing these bacterial cells, these minute, free-floating organisms that have not formed flock and are not native to the system, if they survive things that are smaller than them, like viruses, well, they may not survive things that are bigger than them because they might get eaten up because they're not part of the ecosystem. They've not formed flock. Bacteria in wastewater systems tend to form flock. So in a typical wastewater system, if you looked under the microscope, we're not seeing 1 micron organisms floating around most times. We're actually seeing these organisms congregate in flock of about 50 to 100 microns. In fact, that's the only reason why they can settle in a clarifier, is because they have formed this flock. They are protective. They allow them to intermix, to mingle, to be able to protect themselves in this polymeric matrix. But if we're doing bioremediation, then those microbes are not part of that ecosystem and they could be eaten up. The third challenge we have is if I do bioremediation, the average bacterial cell has the same specific gravity as water. So if I dose it as a liquid, the tendency is it just floats on the surface. And if it floats on the surface, I can only retain those microbes for the hydraulic retention time. However, in any biological treatment system, the solids retention time is always several orders of magnitude higher than the hydraulic retention time. So hydraulic retention time for most systems is in the order of hours. The solids retention time for many systems is in the order of days, sometimes weeks, sometimes even months. The only situations where HRT and SRT tend to be the same is in digesters, where you're not separating solids, you're just putting the solids into the digester, you're mixing the whole thing, and you need about 20, 30 days overall because it takes time for those hydrolysis steps to occur. So how do I make sure, if I was doing bioremediation and I'm bringing all these expensive microbes into a system, how do I make sure they don't just float away? So that's another challenge to deal with. And then the fourth one is, how do I make sure that when I introduce these microbes that are supposed to enhance the system, we can get them integrated into flock within the time frame that we have for the hydraulic retention time. The way that so this led me to my work in Drylet, and what Drylet did was, rather than just dose microbes directly into a wastewater treatment system for remediation, they would actually just embed the microbes inside a porous media. So the porous media would be some type of metallic oxide, highly adsorptive, and normally food-grade material, so things like silica oxide. And the microbes would be embedded. And the advantage that provided was, by protecting the microbes inside the media, you are protecting it from things like phages and predation organisms. So these media are about, typically 100 to 600 microns in size, so much bigger than some of the things that want to feed on the microbes. That protects them. The other thing is, because the microbes are inside of the media in this biofilm environment, it becomes very difficult they're very resilient. I think the best example of biofilm resiliency I can imagine is the fact that we brush our teeth every day, and yet we can't kill the microbes that are in our mouth, because they are in a biofilm form. And the biofilm form also offers remarkable advantages. Now we know there's something called quorum sensing. Now we know that there's lateral gene transfer within a biofilm environment. Now we are beginning to understand why all it takes in a biofilm is for one or a few microbes to survive and adapt, and then pass those characteristics and qualities across the entire biofilm environment. So that provides that type of protection. And then the other one is, in this metallic oxide, this stuff doesn't float. It actually, if you have a good mixing, it stays mixed. If the mixing is poor, it falls into the solid phase. So you retain these microbes in this form for the sludge age, for the solids retention time, and not the hydraulic retention time, which allows you to keep the microbes within the system for much longer. And then now that the microbes are within the solid phase for much longer, you're able to integrate much better into flock. So as I indicated earlier, a number of different things to consider when we're looking at microbes. There's a dizzying array of them. There's so many of them we could potentially be bringing in, but there are just so many conditions we have to think about. So the first one is, the pH. Depending on the conditions that we're dealing with, what types of microbes are best optimized for the type of work that we're trying to do. Temperature is also critical. And so in the most resilient systems that I've seen, even if you would see microbes across a broad range of temperature ranges. And as you can see from some of these diagrams, even though the microbes might have optima in specific, so the mesophiles might have a 39 degrees Celsius optimum, but then there's a significant overlap at some point between psychrophiles and mesophiles. So we're typically not surprised when we do genomic analysis and we find psychrophiles even in mesophilic systems, because there is some overlap. It provides us with resiliency. It's one of the reasons why winter comes and our entire system doesn't die off, because as soon as winter comes, it just means that now our population dynamics begins to shift a little bit. And with a keen knowledge of what's going on in the system, we can actually then begin to use things like bioremediation and process modeling to help us optimize what's going on in the system. Another key thing that that I've found extremely important in the work that I've done over the last few decades is what is it that we're trying to achieve? And when I started out, my interest was in the dissolved oxygen level. I've since found that it's not a helpful parameter. What's more important is, what is the ORP? what is the oxidative reduction potential of the system? Because the ORP, as we can see in the diagram below, gives us a good understanding of what the electron acceptor is likely to be in that environment. There are very many different types of electron acceptors. Carbonaceous organics can be electron acceptors, sulfates, nitrites, nitrates, oxygen itself. And so once we start going into things like nitrification, denitrification, we have a keen understanding that we're trying to stay around this anoxic zone, because if we're not in the anoxic zone, if the conditions are not anoxic, then our microbes are never going to utilize nitrates as an electron acceptor. They would always prefer to go to the materials of a higher ORP, that ORP environment. So if I want to do denitrification and I want to remove nitrogen, then I know that I must force my system into an anoxic zone. If I'm trying to do things like, anaerobic digestion, then I know that my ORP as a control element has to be more reduced. And so, the ORP as a control variable is something that I've learned, has even more importance than the oxygenation state of the process. A DO of 0 might be an ORP of 0. A DO of 0 is also an ORP of minus 400. You have no idea what the ORP is if all you're doing is tracking what the oxygenation state is. But by understanding the ORP, we can actually choose and select exactly what type of dynamic and what type of electron acceptors we're utilizing in the process. And so in the work that I've done, we've worked across very many different types of environments. We've done work in soil with oil spills and had to degrade hydrocarbon materials. We've worked in large lagoon systems, industrial systems, where, as you can see in the second image, you just have this is a rendering plant where they're dealing with slaughtered animal waste. And there's just a huge amount of fats, oils, and grease that just sits on these basins. And what you're seeing here is one of my colleagues actually spraying that biocatalyst material in order to be able to break down that high gunk organic material. And the image that I have showed below is what it looked like when that spraying began, and what that system looked like about 8 weeks later, where the microbes that you're spraying over the material is actually enabling you to begin to break down the lipophilic and hydrolytic, they're generating lipophilic and hydrophilic enzymes that are breaking down those solids and allowing the system to be, to essentially have an enhanced capacity for treatment. Sometimes we dose directly into the basin. We do a lot of work with lagoons, lakes, rivers, streams, septic systems, home-based septic systems, just wherever microbes are being utilized. One of the things that I've learned is we can actually understand, as soon as we understand what's going on in that system, without engineering anything else, there's a possibility that we can actually get treatment enhanced. So there's a broad range of things that bioremediation could be applied for. Traditional wastewater treatment system, improving performance in wastewater treatment systems, as you see in case 2, increasing biogas generation, whether in the context of large digesters, small digesters, farm-based digesters, mixed waste digesters, small septic systems in people's homes. It doesn't matter what the system is, as long as we're using microbes, they can possibly be enhanced. And then we also have also done a lot of work in concentrated animal feed operations. Dairy farms, swine farms, hog farms, things like that, where you're generating a significant amount of agricultural waste, both manure as well as crop residue, and you're trying to break that down because you got to do something with those solids. And then one of the other interesting applications is things like remediating algae. So anytime we see algae, it's a competition for nutrients. So we have nitrogen, we have phosphorus. The good news for algae is they don't need organic carbon. As long as there's inorganic carbon, there's alkalinity and CO2, the algae will grow. So if you're trying to knock algae out, then it's either you make sure there's no nitrogen and phosphorus, which can be very difficult, because it means now you need treatment processes that remove nitrogen and phosphorus, or you stop runoff, or you introduce microbes that will compete with the algae for the nitrogen and phosphorus. And that's the approach in this particular instance. In case number 6 might be a little difficult to see, where the pond, a lake that was being used by divers, was overrun by algae. And the strategy here was to go in and outcompete the algae by introducing microbes that could compete for the nitrogen and phosphorus within the system. So one of the things that I've seen happen a lot more in the last, certainly in the last decade, is when we think about bioremediation, I am seeing, so when it comes to bioaugmentation, the work that I've done has mostly been focused on natural cellular bioaugmentation. So we've gone back into nature. We've looked at microbes that are naturally in water and in soil, and then we've taken those microbes that we know have some specific functions, and we've incorporated them into things like that metallic oxide platform, put them into systems. But what we're starting to see now is we're starting to see a lot of genetic bioaugmentation. We're seeing companies like Alonia and LanzaTech and Ginkgo Bioworks actually look at molecules they want to treat and then engineer microbes that can help, that can treat those systems. I have a bias for natural systems. I think there's a limitation. I am always wary of introducing new things into the natural environment. But this is just an area of work, of more work that I'm starting to see happen now. And then what I'm seeing a lot more, and I'm also starting to do some work in this space, is a lot of my focus historically had been on using microbes and having those microbes actually generate the enzymes that you need. But then there are companies that actually isolate enzymes. And you can also, in the same way that you're introducing the microbes, introduce some of these enzymic elements into processes to enhance treatment. So it brings me to 2 slides that will end this discussion. So the first one is rethinking water treatment. If we think about sewage, the strange thing about sewage is the average human being excretes about 0.03 gallons of feces a day. We also generate somewhere between 0.5 to 1 gallon of urine. These are the sources of waste, the major sources of waste at a household level. So in the United States, the average sewage generated per person is about 100 gallons of sewage per day. And what we're basically doing is we're taking 1 gallon, combined gallon of waste from urine and feces, and then we're diluting that with 99 gallons of what is arguably almost clean water from flush, from wash waters, and that's what we're sending to these big treatment plants. So if I was going to rethink how to do sewage treatment, and we've done that because that's just the way we've always done it. So we use almost 4 gallons, sometimes anywhere between 1 to 4 gallons per flush. We take these long showers. You're only washing yourself for maybe 1 minute, but the shower is on for 10 minutes. And all that water is wasted. We're doing laundry, and we're using almost 50 times the amount of water that's going to be required in these laundry systems and machines. So if we were rethinking how we fundamentally did water treatment, maybe we don't need to have this dilution, because what this dilution does is it turns something that should be a high solid stream that, so if we think about sludge age or hydraulic retention time, the volume I need to hydraulically retain 0.03 gallons or 1 gallon, right? If I need 1 day of hydraulic retention time, now I'm forcing myself to have 100 times the volume that I need to have a 1 day hydraulic retention time, because I have diluted the stuff by almost 100 times. Now, there are some advantages to the dilution. It makes it a little easier to move. it might, but it makes it also less concentrated. So from a mass transfer perspective, my concentrations are lower when I've done all this dilution versus where I have this more concentrated system. So could we actually do source separation? Could we reduce how much we're diluting this waste by? Could we take some of these fecal waste, which is small volume, at the household level, use things like anaerobic digestion to stabilize that waste, generate some biogas, even at the household level, maybe use it for a little bit of cooking or some minimal energy provision, and then take the stabilized fertilizer and use that at some level for crops. Could we take the urinal waste? 75% of the nitrogen we're concerned about comes from urine. So could we take that urinal waste, separate it, not mix it in with everything else, because that's the complication. That's one of the reasons why our treatment plants need to be bigger and bigger, because we're trying to do nitrification and denitrification. The urine itself, if it's stabilized, can be a very rich source of liquid fertilizer. And then could we take this relatively clean water from wash waters and dishwashers and things like that, and just do some minimal treatment at a household level and utilize it as gray water? Could we take that stuff and use it to flush toilets rather than clean water as a flush? So these are some things that can be done. I've actually been fortunate to be involved in a number of projects almost 20 years ago now, where in Brazil, where we were providing these types of services to high-rise buildings, where we were taking their wastewater, treating it in the basement using membrane bioreactors, and then taking the water generated from that, and that was what was used in their flush systems. So they didn't use clean water to flush, they used this recycled water from their own treatment systems for flush water. So that's one way to think about it. The other fundamental paradigm shift that I think we also need to consider is that should we even be talking about waste treatment? You know, I argue that our wastewater treatment plants should be biorefineries, right? You know, we started with treatment. The goal initially was just let's clean the water. And then there was this move in the 1990s to, you know, to the early 2000s that was focused around, we know there's a water energy nexus. We know that somewhere between 2 to 4% of all the energy used in a municipality is for just pumping water. You pump the water to a wastewater treatment plant. You pump the water from a drinking water treatment plant. We're just pumping all this stuff, and it's almost 4% of all the energy we utilize. Do we need to do that? Can we rethink the way that we do it? And then we have all this richness in waste that we're struggling to deal with. But the reality is it's immensely rich. We complain that we don't have enough phosphorus in the world, but there's enough phosphorus locked up in our feces that we may not need to actually mine new phosphorus ever. We have enough gold falling, you know, in the feces that if we had ways of being able to extract those materials, there's so much, you know, that we could mine from sewage. And so if we reimagined what the treatment of the future could be like, could we have wastewater treatment systems that actually don't need, and the effluent from the wastewater treatment plant is what feeds our drinking water treatment plant, because there's no need for us to be pumping wastewater and put out almost clean, right? Almost clean water. In some cases, the effluent from a wastewater plant is actually cleaner than the source water we're taking from a river or lake to a drinking water plant. Could we do that with some additional treatment, obviously, to remove any remaining contaminants of concern? Could we take leverage anaerobic digestion as much as possible? Reduce the dilution factor so we can have smaller, more compact reactors. So we're generating energy, we're taking the nutrients that are generated, the digestate, and we're turning that into organic fertilizer. These are possibilities that we can actually explore. Could we take the CO2 that is generated from the treatment processes and then leverage that CO2 and utilize it in methanotropic or methylotropic systems that can take CO2 and methane and turn that into bioplastics. These are possibilities that can actually be explored. And so right now I'm spending a lot of my time trying to explore those possibilities. And I think there are 6 challenges that we need to address as we think about this new age possibility. The first one is, the biggest challenge we have is these biosolids they are rich, they are nutrient rich, they are carbon rich, but they are not soluble. So how do we access that carbon? We need to lyse the cells. We need to blow the cells open. We need to get into the COD that's locked up in these cells, in this cellulosic or lignocellulosic material, in the biosolids. How do we access that? We need new lysis methods to be able to do that. How do we enhance the cost and the efficiency of digestion? We use about 20 to 30 days to do digestion. It's inefficient. And after doing digestion for 20 to 30 days, you're lucky if you have actual 50% conversion of the carbon locked in the digester, because it can be a very difficult process. The solid concentrations are so high that there's significant mass transfer limitations. So how do we boost that process? That's also something that we need to unlock. We have all these possibilities to utilize algae for CO2 capture. Struvite right now, anybody who runs digesters, it's a nuisance. We're generating all this struvite, but this stuff is actually rich in nitrogen and phosphorus. How do we optimize those systems so that these nuisance materials that are now impediments to efficiency can actually become products that we generate? How do we do things like methanotropy? How do we take products like methane, products like CO2, that right now in some cases are wastes, they are flared? How can we take them and turn them into bioplastics? How can we turn them into new biofuel sources? We know this is possible. We're doing this at a pilot and lab scale. But how then, it leads me to point number 5, is how do we create business models that allow us to take all these possibilities that we're playing around with on spreadsheets and turn them into viable things that can be sold, that can stand alone as businesses and solutions that we can bring to the table? And then how do we create partnerships that take some of these new materials that we're generating, the single cell organisms that we're using waste CO2 to generate? How can we turn them into things like animal feed proteins and things like that? And the good news is there are actually companies that are starting to emerge that are actually beginning to do this. So we have companies like Mango Materials that is taking animal feed proteins manufactured from CO2, and they're using that to replace proteinaceous material in animal feed. We have companies like Unibio that are using algae to generate bioplastics, PHAs and PHBs that are starting to replace the use of fossil fuel-based plastics. All of these are still in their infancy, but I believe that the next phase of growth is us beginning to think of not wastewater treatment, but actually biorefining. The treatment system as a biorefining unit where we're generating energy and we're generating products. In conclusion, what I've learned in my 2+ decades in this industry is that biology is remarkably efficient and cost effective. And that if we understand biology and we understand microbes and we understand the limitations of these treatment systems and don't try to force them to do more than they're supposed to do by engineering them to be even bigger and more monstrous, that just understanding that simple biology can help us be much more efficient, can help us understand what we can't change, and then leverage what we have to be able to address the goals and the targets that we want. I've also learned we need new tools. Genomics is something, when I started in the business, 20, 30 years ago, we weren't using DNA analysis. We didn't even talk about the differences in the types of microbes. Now it's routine. There's no plant I would go to today where one of the first things I'm doing is not a genomic analysis to really understand what microbes are present and to understand why we're seeing the type of things that we're seeing. And then the last 2 things I would close with is the fact that as I come from Nigeria. It's a developing economy. India is also is also developing. There are, and as we continue to build new treatment systems, I think we have the advantage of leapfrogging some of the things that the developed world, that folks like the US and others did. They started doing carbon removal and then found out over time that they needed to do things like nutrient removal. And so their plants evolved to deal with that. I think the advantage that the developing economies have is we know what all these problems are. So we can sit down and we can optimize and think about what the best solutions are as we bring those solutions to the table. Decentralization makes sense. We have to rethink the way we imagine plumbing in a house. We have to stop this process of using clean water to move bad. We have to think about decentralized treatment, even at a household level, as a fundamental part of how we think about building facilities. And then we also have to think about, I think, the notion that treatment plants are not waste treatment plants, that they are actually biorefineries where we can generate materials, we can generate energy, we can clean the water for sure, but it's not a waste treatment system. It's actually a biorefinery system where we're generating high value products. So thank you very much. I apologize if I had significantly exceeded the time that was given to me, but so apologies for that.
You did significantly go beyond the time limit, but I must tell you that this has been one of the most fascinating
experts on the call here, and we know each one of you has perspectives on this. We invite you to continue the conversation through the Global Waterworks community, but also to include your questions right here and just keep them brief so that we can get in as many as possible, because there are so many perspectives on this. And Malcolm, it's 100 years of history, innovation that's needed. So very thorough presentation. And we thank you for your taking the time, and also the beautiful case studies which prove out what was there. So Ravalji.